Section 1.3 Basic Definitions needed to describe thermodynamic systems. What is a system? A system is any matter you study. What is surroundings? That's simply the rest of the universe. So, the sum of the system and surroundings is the universe. If you try to study a computer, that computer is the system. The rest of the universe is the surroundings of that computer. There are three different types of systems in regard to matter exchange and energy exchange. There is matter exchange and energy exchange between an open system and its surroundings. There's no matter exchange between a closed system and its surroundings, but it's possible to have energy exchange between a closed system and its surroundings. For an isolated system, there's no matter exchange, there's no energy exchange. For example, soda in a rigid, well-insulated container. Rigid means there's no way for the surroundings to do work to the system or vice versa. Well insulated means there's no heat flow. There's no heat across the boundary between the system and the surroundings. So what is a boundary? Again, the boundary is the interface between the system and its surroundings. If you imagine the computer in front of you is the system, and then you have to imagine an interface between the computer and the rest of the universe. That's the boundary. Walls are physical boundaries that you can see. So walls can be rigid or movable. It can be a real wall. It can be permeable or non-permeable. Permeable means the wall may allow some molecules to pass through. A wall can be adiabatic or diathermal. Adiabatic means heat cannot transfer across the wall. Diathermal means heat can transfer. So to make an isolated system, you need a physical boundary. That's adiabatic. So in short, you need a adiabatic wall. Now we're going to talk about extensive versus intensive properties. Extensive properties are proportional to the size of the system. For example, the mass, volume, energy, kinetic energy, potential energy, or number of moles. For example, if you have 2 cups of water versus 1 cup of water, the mass of 2 cups of water is twice the mass of 1 cup of water. Therefore, we can see the mass of the system is proportional to the size of the system. Mass is extensive. So is volume. 2 cups of water has a larger volume, 100% larger than 1 cup water. Same for energy, kinetic energy, potential energy. You may imagine every single water molecule has a certain amount of energy, and if you have twice the number of molecules, you have twice the amount of the energy. Intensive properties does not depend on the size of the system. For example, molar mass. Water has a molar mass of 18 grams per mole. If you have 2 cups of water, it's 18 grams per mole. If you have 200 kilograms of water, the molar mass is again 18 grams per mole. If you have only 1 drop of water, the molar mass is the same, 18 grams per mole. Similarly, molar volume, molar energy, kinetic energy per atom or per molecule are all intensive properties. They do not depend on the size of the system. Another good example is density. That's mass over volume. Again, the density of water does not depend on the amount of water. So it's temperature, pressure, and concentration. Again, when you have 2 cups of water being compared with 1 cup of water under the same condition, they have the same temperature, same pressure, they feel the same pressure, and they have the same concentration. Over here it tells you some just basic rules, extensive properties versus intensive properties. So if you have extensive plus minus extensive, you get extensive. If you have intensive properties plus minus intensive properties, the result is intensive. You never add one extensive property and one intensive property together because it's ridiculous. If you have a extensive property divided by extensive, you get intensive. Extensive divided by intensive, you get intensive. So I want you to imagine this extensive is proportional to the number of moles n. Okay, so on the left hand side, it's proportional to the number of moles of n. On the right hand side, it's also proportional to n. And over here, extensive over intensive. So this is proportional to n, this is not, therefore the result is proportional to n. However, if you have extensive divided by extensive, on top it's proportional to n, on the bottom it's also proportional to n. These two n's cancel, therefore the result is intensive. Alright, so again, if we come back to this PV equals nRT for ideal gases, P is intensive, V is extensive, so the product of PV is extensive, nRT. N is extensive, R is not, T is not. Therefore, N times R times T is also proportional to N. nRT is extensive. So PV is extensive, nRT is also extensive. Over here, this is to show you how to calculate the molar concentration of pure water. You can just click this website and you will see the calculation. And also you can see the concentration of water does not really depend on the size of the system or the amount of water. Equilibrium, it's just a state of balance between opposing forces or actions. So if you simply sit still in front of the computer, I believe there's an equilibrium between the gravity and the upward force provided by your chair. A system is in equilibrium with its surroundings with respect to a variable. It can be pressure, temperature, concentration, and it can be all of them. All right. So there are different kind of equilibrium. What's thermal equilibrium? That's just equilibrium with respect to temperature. The zeroth law of thermodynamics states that if A and B are in thermal equilibrium, and B and C are also in thermal equilibrium, then A and C are also in thermal equilibrium. You can replace thermal equilibrium with like pressure equilibrium. I think this statement holds true as well. What is a thermodynamic equilibrium? Well, you have to look at three variables: pressure, temperature, and concentration. All right, so all three intensive properties are the same inside the system, and then we can say everywhere inside the system, and then we say the system has reached the thermodynamic equilibrium. Now let's look at the units of pressure, volume. Pressure, the unit is Pascal. 1 Pascal is 1 Newton over 1 square meter. The SI unit of volume is cubic meter. And 1 Pascal times 1 cubic meter is simply 1 joule. There are some other commonly used units in thermodynamics. 1 bar is 100,000 pascals. 1 ATM is slightly greater than 1 bar. It's 1.01325 bars. 1 ATM is also 760 torrs. 1 liter is 0.001 cubic meter. 1 milliliter is 0.001 liter. And it's 10 to the power of negative 6 cubic meter. 1 decimeter, 1 cubic decimeter is 1 liter. So these two are exactly the same. All right. This is because 1 decimeter is 0.1 meter. 0.1 meter to the power of 3 is 0.001 cubic meter. In this course, I encourage you to use the SI units whenever you can, whenever it's convenient. But sometimes, if you choose to use non-SI units, fine. Just use them consistently. Alright, so if you use liter as the unit for the volume of A, and then use liter for the volume of B, C, and D, or other systems, do not mix different units together. It's gonna cause headache and of course errors.